Welcome back to the second part of my talk for the Nearly Carbon Neutral Geometry and Topology Conference. In the first half, we saw a bunch of examples of discrete subgroups of semisimple Lie groups of SLDR, and we asked if we could find a nice class of discrete subgroups that includes these examples. And then we looked at some features of the symmetric space associated to these Lie groups. Looking at features of the symmetric space tells us about the space where our discrete subgroups gamma will live. On the other hand, there are conditions we could impose on these gamma as abstract groups. For instance, we could ask for gamma to be delta hyperbolic. I'm going to look at a slight generalization of or weakening of delta hyperbolicity called relative hyperbolicity, which I'll introduce now. The idea behind relative hyperbolicity is that the group is basically delta hyperbolic, except along isolated subgroups where that hyperbolicity might break down. More precisely, suppose gamma is a finitely generated and torsion-free group. And again, the torsion-free assumption is not essential, but it helps make things less technical. Curly P is going to be a finite monormal collection of finitely generated subgroups of gamma. And here monormal means that any two distinct conjugates of subgroups in P intersect only in the trivial subgroup. Curly P is going to be the collection of subgroups where the hyperbolicity breaks down. We will also call these the peripheral subgroups. And the monormality condition is a way of making precise the idea that we want these subgroups to be isolated from one another. None of these tons of maximal sets intersecting all over the place like we see in a higher rank symmetric space. Given this data of gamma and curly P, we can form a metric graph C, which we call the cusp space. And the space is given by taking a Cayley graph for gamma for a suitable generating set, which I'm suppressing here, and gluing in a combinatorial horoball over each left coset of each peripheral subgroup. What's a combinatorial horoball? It's a metric graph whose vertex set is given by the group that you're forming the horoball over across the positive integers. So we're going to glue it into the corresponding Cayley subgraph along the bottom level of vertices. And there's an exact definition for these things. It's maybe not that enlightening, so let me rather just tell you some key properties. So these combinatorial horoballs, they are always delta hyperbolic, and their Gromov boundaries always consist of a single point, no matter what P you start with here. And moreover, they model the geometry of horoballs in negatively curved symmetric spaces. So for example, if you take a free abelian group, the combinatorial horoball over that is going to be quasi-isometric to a horoball in real hyperbolic space. If you take the combinatorial horoball over a Heisenberg group, you're going to get something that's quasi-isometric to a horoball in complex hyperbolic space. And you can imagine, for instance, take gamma to be the fundamental group of a cusp torus, and curly P to consist of the cusp subgroup. Then if we put a hyperbolic metric on the cusp torus, you can imagine the Cayley graph as sitting inside the hyperbolic plane, except it's going to miss these large chunks that correspond to horoballs that are lifts of the cusp. And gluing in the combinatorial horoballs is going to fill in those blank spaces where the missing horoballs are. So far, I haven't said anything about hyperbolicity or relative hyperbolicity, and indeed we can build a cusp space once we have gamma and curly P as above without any hyperbolicity requirements. If we do this construction, and the space C that we get turns out to be delta hyperbolic, like in the case of the cusp torus, then we say that the group gamma is hyperbolic relative to the subgroups curly P. And this is one of many equivalent definitions of relative hyperbolicity. I'm going to use this one because the space C gives us a concrete handle on the relatively hyperbolic geometry, which allows us to quantify avoiding intersections of maximal flats in a way that's adapted to this geometry. And here's one tool to help us do that. So this space C is a metric graph. We can take the path metric, D sub C, and we're going to define the cusp word length of a group element gamma, which we write this way, as distance from the identity element to gamma in this metric D sub C. And this is, I'm going to think of it as like word length, except if you go along a peripheral subgroup, it's going to get exponentially shortened because now you can take these shortcuts that go through the combinatorial horoball. Okay, something else that relatively hyperbolic groups have that will be useful to us is a good notion of boundary. So if gamma is hyperbolic relative to curly P, then there's a topological space, sometimes called the Bowditch boundary, associated to gamma and curly P, which can be defined as the Gromov boundary of any cusp space, which, remember, is going to be delta hyperbolic if our group is relatively hyperbolic. There are choices involved in the construction of C, but it is a theorem of Bowditch that this boundary is well defined after homeomorphism, independent of those choices. For example, for this cusp torus group example, the cusp space is quasi-axiometric to the hyperbolic plane, and the Bowditch boundary we can see as the boundary circle of the hyperbolic plane. When we have no peripheral subgroups, C is going to be exactly the Cayley graph. There are no combinatorial horoballs. The cusp word length is the usual word length, and gamma being relatively hyperbolic relative to the empty set is exactly the same notion as gamma being delta hyperbolic. And in this case, the Bowditch boundary is the Gromov boundary of gamma. So those are all the characters in the story. And now we're going to throw all of them together and have them do stuff for us. So more precisely, we're going to use relative hyperbolicity and singular values and boundaries to define our nice class of discrete subgroups of D groups, which described our earlier examples. So here we go. Gamma is again going to be a finitely generated torsion-free group. Curly P is a finite mononormal collection of finitely generated subgroups of gamma, which we'll continue to call the peripheral subgroups. And, okay, definition theorem. Also attributions. So when we have no peripheral subgroups, so when we're talking about delta hyperbolic groups and Gromov boundaries, this is going to be work of various people whose names are going to appear below. When we do have peripheral subgroups, this is something I did in my thesis and various extensions of it. And there's also work of Karpovich and Lieb, which formulates similar conditions in somewhat different language. Okay, so a representation rho from gamma to SLDR or PSL or PGLDR is P1 Anosov relative to curly P. And just a short note, this P1 indicates the particular sort of maximal flat we're going to avoid, and also which flag space boundaries we're going to look at. Don't worry about it if it bothers you. This representation is Anosov relative to curly P if one of the following conditions holds. And you can think of the first condition, the first characterization as being the definition, and the equivalence to all the following conditions as being the theorem. Okay, so first characterization, the ratio of the first and singular values of rho of gamma grows uniformly exponentially in the cusp word length of gamma, meaning there are constants C and mu, which make this inequality hold for all elements gamma in the group gamma, plus some conditions, mild conditions on the peripheral subgroups in their images. So this first condition on the singular value gaps, I'm going to call B minus. It's a precise sense in which the image subgroup is avoiding some particular intersections of maximal flats in the symmetric space in a uniform way. And notice I haven't said anything about relative hyperbolicity in this characterization. It's not required. In particular, it's going to follow from these conditions that the group gamma has to be hyperbolic relative to curly P. Given that these conditions on the peripheral subgroups constrain these subgroups so that they don't violate some of the properties that peripheral subgroups of relatively hyperbolic groups must have. And the additional conditions on the peripheral on the images of the peripheral subgroups essentially says that these peripheral subgroups get sent to subgroups of SLDR that have some features of cusp subgroups of rank 1 groups like SL2R. In the non-relative case, so when we have no peripheral subgroups, this first definition was first given in different language by Karpovich, Leib, and Porti, and later formulated in these terms by Bocchi, Potri, San Marino. Okay. Second characterization, we say rho is P1 Anosov relative to curly P. If gamma is hyperbolic relative to curly P, the same singular value gap condition B minus is satisfied. And instead of the additional conditions on the images of the peripheral subgroups, we are going to require that there exist good limit maps which take the dynamics of your relatively hyperbolic group acting on its Bowditch boundary and make them show up in the projective space and the dual projective space via the action of the image subgroup. So in symbols, the condition is that there exist maps C and C dual from the Bowditch boundary to projective space and dual projective space. And good means that these maps are continuous, they're equivariant, and they're transverse, which is a stronger version of requiring that the maps are injective. And in the case when there are no peripheral subgroups, this characterization was first due to Guichard Wienhard. Let me say a little bit more about these first two characterizations in the case when d is equal to 2. So when d is equal to 2, this B minus condition on the singular value gaps is a kind of quasi-isometric embedding condition. It's equivalent to saying that the image subgroup is quasi-isometrically embedded with respect to the metric from the cusp space. And one can check that this is the same as requiring that the image subgroup is geometrically finite in SL2R. Or when there are no peripheral subgroups, the cusp space is the Cayley graph with the word metric, and then the D minus condition is equivalent to the image subgroup being convex cocompact. When D is bigger than 2 or in higher rank, this D minus condition is strictly stronger. So there are representations where the orbit maps give quasi-isometric embeddings, but which don't satisfy this D minus condition. Okay, and then a little bit about the limit maps. So when D is equal to 2, the projective space, also the dual projective space, you can identify with the boundary circle of the hyperbolic plane. And given a geometrically finite subgroup, say a surface subgroup, we can see the limit map associated to it as follows. So given a point X in the boundary of the group, you can take some sequence of points in the group that converges to X that corresponds to some sequence of orbit points in the hyperbolic plane. And that sequence of orbit points is going to converge to some point in the boundary of the hyperbolic plane. And that point in the boundary is where our limit point map sends X. Even better, you can think of the projective model of the hyperbolic plane. So now we draw our hyperbolic plane as a disk in the affine chart of the real projective plane. So now the group we are working with is, well, some subgroup of PGL3R. And now one limit map to the projective space again takes X in the boundary of the group to the limit point of a corresponding sequence of orbit points, just like previously in the hyperbolic plane. And the other limit map to the dual projective space is going to take our boundary point X to the unique projective line that's tangent to the hyperbolic disk at that limit point. So this projective line, remember, represents a hyperplane. So it's a point in the dual projective space. And then the transverse condition in this case says that if you have two distinct limit points, two distinct boundary points, the limit projective point at one, which represents a line, is not contained in the limit projective line at the other. So the hyperplane that the projective line represents is transverse to the line which the projective point represents. Okay, so what's the point? The limit maps, maybe should have said slightly earlier, the dynamics of a relatively hyperbolic group acting on its Bowditch boundary encodes some amount of negatively curved behavior. And these limit maps help capture some amount of this in the image subgroup. Okay, so there are also two other characterizations, 1 lambda and 2 lambda, which are similar to 1 and 2, except we replace the D minus condition on singular value gaps with an analogous condition on the ratios of eigenvalues, which I'm going to call D minus lambda. This says that the ratio of the moduli of the two largest eigenvalues goes uniformly in some stable conjugacy invariant version of cusp word length. So that's what that is here. And since moduli of eigenvalues are asymptotic versions of singular values, this D minus lambda is an asymptotic version of the condition that our subgroup is avoiding certain intersections of maximal flats. And in the case where we have no peripheral subgroups, 1 lambda is due to Cassel 3, and 2 lambda is due to Guichard Wienhard as well. And finally, this one is partly work in progress. One can weaken the D minus singular value condition in characterization 2 to just require that the singular value gap goes to infinity as our elements go to infinity, not necessarily a priori at any uniform rate. And the price we pay for that is that we have to assume slightly more for the limit maps. We have to also assume that the limit maps extend the orbit maps, like what I've described in the examples in the hyperbolic plane or the projective model of the hyperbolic plane. And these here in red are some terms that are used to describe this condition of extending the orbit maps in the literature. And in the non-relative case, this last condition was formulated by Xabalas. All right, so that was one big definition theorem. What are some examples of these subgroups? So all of the ones we talked about earlier, in particular, geometrically finite subgroups of PSL2R are examples. And in fact, being P1 relatively Anosov in PSL2R is equivalent to the image subgroup being geometrically finite. Geometrically finite convex projective structures on D-1 manifolds, which I've given you a general description of, though not quite a precise one, give discrete subgroups of PGLDR. And the inclusions of these into PGLDR are P1 relatively Anosov, again, relative to the subgroups corresponding to the cusps, the controlled non-compact ends. Hidden representations are P1 Anosov relative to no peripheral subgroups, as was mentioned earlier when we talked about them. And we can also define similarly representations of free groups in PSLDR by taking a surface with that free group as the fundamental group and taking a representation into PSL2R given by a cusped hyperbolic structure, and then composing this with the irreducible representation in the PSLDR and deforming the image subgroup while preserving the conjugacy classes of the parabolic subgroups. These representations are no longer P1 Anosov because of these parabolic elements, but they are relatively Anosov relative to these parabolic subgroups. One can also obtain other examples, for example, by playing ping pong in a projective space. And it's maybe not immediately clear how you prove that these things are examples. It's a helpful exercise if you want to think more about these ideas to figure out how to do it. And I will say it's often the characterizations with the limit maps which are easiest to establish for many of these examples. In general, whenever we have a relatively Anosov representation, it is discrete and faithful, and the orbit maps give quasi-isometric embeddings of the Cayley graph, though not with the word metric. You have to take the induced metric it gets from being a subspace of the cusp space. This space is quasi-isometrically embedded into the symmetric space. And this proposition more or less follows immediately from the minus singular value gap condition. Because distances in the symmetric space, you can compute in terms of logarithms of the singular value gaps. So that's one of the two things we were looking for. What about stability under perturbations? So when we have no peripheral subgroups, Labourie proved that the set of P1 Anosov representations of a given abstract delta hyperbolic group is open in the space of all representations from the group to SLDR, or PSL or PGL. So you can wiggle your Anosov representation or subgroup a little bit, and the result will still be Anosov. To prove this, Labourie used a different equivalent definition of Anosov representations, given in terms of uniform contraction on flat bundles over suitable flow spaces. And this definition is the original one, actually. It's also where the name Anosov comes from. But I haven't stated it here because, as you might have realized, it takes a lot more time and work to actually state. Recently, Canary, Zhang, and Zimmer have shown a similar result when gamma is the fundamental group of a cusp hyperbolic surface, and curly P is the collection of cusp subgroups. And in this case, they prove that the set of representations, which are P1 relatively Anosov, relative to this curly P, is open, not in the space of all representations, but rather in the subspace of representations where these parabolic subgroups, peripheral subgroups, get sent to prescribed parabolic conjugacy classes. And to do this, they used also a flow-based definition for relatively Anosov representations, which generalizes Labourie's definition for Anosov representations. In work in progress with Andy Zimmer, we are trying to generalize this to more general relatively hyperbolic groups. And the relative case is trickier than the case when we have no peripheral subgroups, basically because the flow space we work with is no longer compact, and more care is needed in many places when compactness previously just took care of things. So here we really need to use some sort of finite geometric control we have on our cusps, on our non-compact ends. So in short, we have a class of relatively hyperbolic discrete groups of SLDR, discrete subgroups of SLDR, which generalizes the notion of geometric finiteness in SL2R. And the title of the talk says a notion of geometric finiteness because there might be a bigger, better notion to be found. This one that we have is still quite attached to the non-compact ends looking like cusps from negatively curved symmetric spaces because of the combinatorial horoballs that we use. So if anyone has any ideas or really has any examples to play with, I'll be really happy to hear about them. And that's all. Let me say before I leave you that questions are really welcome, and I really look forward to hearing from you and talking to all of you on Discord or Zoom. Thanks for listening.